7.6 Vertex form of a quadratic function. Our goal for this section is to be able to graph a quadratic function in the form y is equal to a times x minus h squared plus k, and relate the characteristics of the graph to its equation. So we learned that the vertex form of the equation of a quadratic function is written like this. The graph of the function can be sketched more easily using this form. You need to know that a quadratic function that is written in vertex form has the following characteristics. The vertex of the parabola has the coordinates h, k. The equation of the axis of symmetry is x is equal to h. The parabola opens upward when a is greater than 0, and the function has a minimum value of k when x is equal to h. The parabola opens downward when a is less than 0, and the function has a maximum value of k when x is equal to h. A parabola may have 0, 1, or 2 x-intercepts, depending on the location of the vertex and the direction in which the parabola opens. By examining the vertex form of the quadratic function, it's possible to determine the number of zeros and therefore the number of x-intercepts. If it opens up and it's below the x-axis, we're going to have 2 x-intercepts. If we have 1 x-intercept, it's going to just touch the x-axis, and if the vertex is above the x-axis, we're not going to have any x-intercepts if it opens up. Let's do an example. Sketch the graph of the following function. F of x is equal to 2 times x minus 3 squared minus 4. State the domain and range of the function. We know a is greater than 0, so our parabola opens up. The vertex is at h, k. Remember, our vertex form is f of x is equal to a times x minus h squared plus k. We can then find what our vertex is going to be. The vertex then is at h, k. So our vertex is going to be, h in this case is 3, k in this case is negative 4. So that's where our vertex is. And the equation of the axis of symmetry is going to be x is equal to 3. And then we still need to determine one other point on the parabola. Let's substitute 0 in for x, because that's always easy. So f of 0 is equal to 2 times 0 minus 3 squared minus 4. F of 0 is equal to 2 times negative 3 squared minus 4. That's equal to 14. So point 0, 14, is on the parabola. We can easily sketch from here. So I start off with my axis of symmetry, and I label my axis of symmetry x is equal to 3. The next point I plot is my vertex, with the point 3, negative 4, which I got that from h, k. Then I have 2 points on my parabola. I have point 0, 14, and because my vertex is 3 away from that, I know that I have another point at 6, 14, because it's going to be an equal distance away. Then I can sketch my parabola. The domain for this function, x is valid for all real numbers, y for greater than or equal to negative 4, because we have a minimum in this case, and y is part of the real numbers. Randy claims that he can predict whether a quadratic function will have 0, 1, or 2 zeros if the function is expressed in vertex form. How can you show he's correct? So, if we write it in vertex form, f of x is equal to 2 times x minus 2 squared minus 5. I know that my h, k is going to be 2, negative 5. That's where my vertex is going to be. 2, negative 5. So my vertex is actually below the x-axis. Therefore, we're going to have 2 zeros. That seems reasonable. For the next one, f of x is equal to x squared. I can write this in vertex form quite easily. F of x is equal to x minus 0 squared plus 0. Here, it's going to be on the axis because my h comma k is going to be 0 comma 0. So my y is 0 and my x is 0, therefore my vertex is here. So I'm going to only have 1 0 in this case. For f of x is equal to 2 times x plus 3 squared plus 4, my conjecture is that there are no zeros, because my h comma k is going to be negative 3 comma 4. So my h comma k, that's my vertex. My vertex is going to be at negative 3 comma 4. My a is positive, so that means it's going to open up. So my vertex is already going to be above the x-axis, and it's going to open up, so I'm not going to have any zeros. This makes sense. Let's do another example. A soccer ball is kicked from the ground. After 2 seconds, the ball reaches its maximum height of 20 meters. It lands on the ground at 4 seconds. Determine the quadratic function that models the height of the kick. I'm going to let x represent the elapsed time in seconds, and I'm going to let y represent the height. And of course, my height is going to be in meters. So the maximum height is 20 meters after 2 seconds. So my vertex then of x comma y is going to be 2 comma 20. That's the point of my vertex. Then I can start out by writing this in my vertex form. So y is equal to a times x minus 2 squared plus 20. So I've substituted my known values. I've substituted my h and I've substituted my k. Next, I can solve for a by using the point that corresponds to the ball hitting the ground. The ball hits the ground after 4 seconds, so the height is going to be 0. So the point that I'm going to be using then is 4 comma 0. So for 4 comma 0, I can solve for a. F of x, in this case y, is going to be equal to 0. And then I can sub in 4 for my x value. So 0 is equal to a times 4 minus 2 squared plus 20. 0 is equal to 4a plus 20. Isolating, I get that negative 20 is equal to 4a, so a is equal to negative 5. So then the following quadratic function models the height of the kick. F of x is equal to negative 5, that was my value that I found for a, times x minus 2 squared, that's h, plus k, which is 20. Part B asks, determine any restrictions that must be placed on the domain and range of the function. So, time. The time at the beginning of the kick, the time was 0. So that's going to be x is equal to 0. At the end of the kick, the time was 4. The time was 4. So that's x is equal to 4. So then the domain is x such that x is greater than or equal to 0 and less than or equal to 4, because our time didn't go past that, where x is a real number. So then my domain. Oh, sorry. Then I have my range. My range goes from 0, that's the ground, to 20 meters. So I know my range is going to be y, such that y is greater than or equal to 0, but less than or equal to 20, because that was my maximum height, where y is a real number. Part C. What was the height of the ball at 1 second? 1 was the ball at the same height on the way down. Part C. I can substitute 1 in for x. I'll write out my equation. F of x is equal to negative 5 times x minus 2 squared plus 20. Substituting 1 in for x yields f of 1 is equal to negative 5 times 1 minus 2 squared plus 20. That is equal to negative 5 plus 20, which is then equal to 15. So the ball was at a height of 15 meters after 1 second. That occurred obviously as the ball was rising. The equation of the axis of symmetry is obviously x is equal to 2, because that's the x-coordinate from our vertex. So symmetry provides the point, if it was 15 and 1, my axis of symmetry is going to be 2 away from that, so then it should be, 1 and 15, then it should be 3 and 15. So 3, 15 is the other point where the ball is above the ground by 15 meters. So therefore, it was also at 3 seconds. That's when the ball was on its way down. So here I had it on its way up at 1 second. Here I had it on its way down at 3 seconds.